Okay, hello and welcome to the Radical STEM Homework Help Livestream. Uh, so, if you have any homework questions in math or science, then ask them here in the chat. We will do our best to help you solve it live. In the meantime, while we don't have any viewer questions, I will just be working on some random math questions and physics problems. But don't hesitate to interrupt with your own question, because that's what I'm really here for. I think let's do some simple differential equations. We have dy dx being equal to k times y times x minus 1. So this looks like it is a separable differential equation. We should be able to put all the y's on this side and all the x's on this side, and then integrate it and be able to solve for the function y of x. So let's try it. Let's divide by y, get dy over y, and multiply dx to the other side. Get k times x minus 1 times dx, and now we'll integrate. And I guess these are going to be indefinite. So on the left side we have dy over y. That of course is going to be our natural log of y. Over here we can pull this k out of the integral, and then we have the integral of x minus 1. The integral of x, we're going to get x squared, and then we divide by that exponent of 2. Minus integral of 1 times dx would just be x. And we just evaluated an indefinite integral, so we're going to get some constant of integration over here. And now, if we want to solve for the function y, we can raise both sides to e, the exponential function. So that over here would give us y being equal to e to the power of all this junk. So k times x squared over 2 minus x plus c. But we can simplify that. So first off, when we have this addition right here, e to something plus another something is the same as e to the first something times e to the other something. And e to some number is just another number. So really I'm just going to rename that a whole new constant, maybe d. So there'll be some unknown constant in our function based on the initial conditions. And I think that's about all we can really do. Well, let's see. We would get k over 2x squared, and if we broke that up, we would also get e to the minus k times x. But of course something with a negative exponent is really just dividing by that. So that would be e to the positive k times x on the bottom. I'm not sure if that really simplifies anything for us. I guess we could say this is x squared over 2, and this whole thing is to the kth power. I think that's about it that we can do with this. Okay, let's try some that have an initial value for us. Here we'll have dy dx being equal to x times y minus 2 divided by x squared plus 4. And up here I'm going to write we have our initial condition that y of 1 is equal to 5. Okay, so we'll do it again. Get all of these y terms on the left and bring this dx with all of the x terms on the right side, and then see what we can do with it. So we'll divide by y minus 2, get dy over y minus 2 being equal to x squared plus 4 x on top dx, and then we'll integrate. So here we could, do a u substitution where we let u equal y minus 2, du would equal dy, and then we would just be integrating du over u, or natural log of u is the result. So we're going to get natural log of y minus 2. Over here, we'll have to do another substitution. I think we should actually write this one out though. So we're going to let u equal x squared plus 4, the part that's on the bottom. Then du dx would be equal to the derivative of the right side, which is 2x. So bring the dx over here. We'll divide by that 2. And that will nicely swallow up this part of our integral. So this will actually become the integral of, or 1/2 the integral of du over u. So we're going to get a natural log on this side as well. 1/2 natural log of u, which is actually x squared plus 4. And we can almost do that same, or rather we will do the same raising both sides to e trick, or raising e to both sides, exponentiate both sides. But if we can get rid of this 1/2, then we'll just instantly undo both of these natural log functions. So I'm actually going to use the natural log property where we can bring a multiple in front to the inside as an exponent for whatever's inside. So we're going to take that x squared plus 4 to the 1/2 power, or take the square root of it. Now, if we exponentiate both sides, the e and the natural log will cancel out for both of them, so we're just going to get y minus 2 equals this square root of some stuff. Oh, I forgot something, didn't I? That was natural log of this stuff plus c. So yeah, that still is going to work, because that would be e to the natural log of some stuff is the stuff times e to the c, which is just going to be a constant multiple. So what we're going to get is y minus 2 being equal to, I'll call it k this time, since k is not already used in the problem, times the square root of x squared plus 4, and then we'll add 2 to the other side. And now, since we have this initial condition, we can actually solve to find that k. So this says when x equals 1, we'll plug in 1 right there, y is going to be equal to 5. So we know that 5 equals k times, if x is 1, this will be the square root of 5 plus 2. So let's subtract that 2 again. We'll get 3 over here, and then that means k equals 3 divided by the square root of 5, which is a really weird number. And so our final particular solution to this differential equation is, I'm actually going to say it's 3 times the square root of x squared plus 4 over 5, then plus 2. Okay, let's try one more. This one doesn't look as bad. Y over x with y of 2 being equal to 3. Okay, so same thing. We'll bring the y to the left side where the dy is. We'll bring the dx over here where the other x is. So we'll get dy over y being equal to dx over x. And then we'll integrate both sides. And we're just going to get natural logs on both sides. Natural log of y equal to natural log of x plus c. I'm not going to forget it this time. Then we'll raise both sides, or we'll exponentiate both sides. E to something plus something is e to the first something times e to the second something. So we'll just call that some constant k. And e to these things will cancel out. So we'll get y equals k times x. Or it's just going to be a straight line, where k is the slope. Now we can apply our initial condition. So when x equals 2, y will be 3. So we know that 3 equals k times 2. Thus, k equals 3/2. And our particular solution for this is going to be y equals 3/2 x. That one was way quicker than I thought it would be. Okay, there's an interesting one. Well, actually, I'm going to do both. They kind of look like a set. So first we'll do this easier one. It's going to be pretty straightforward. All we're going to do is just bring that dx over here, and then right away we can integrate. So we'll just get y over here equal to, if you integrate x squared, you get x to the third, and we want to divide by the new exponent, plus k squared times x plus some constant. So having dy dx equal to x squared plus k squared give us a really simple and fast solution. But here's the one that actually caught my eye. What if dy dx equals y squared plus k squared? Now it's a whole different ball game. So, usual procedure, we'll get our y's on the same side as dy, and we'll bring dx to the other side, and of course there's nothing else over here. Why did I put the big space there instead of on the other side of the equals? Who knows? So this side is just going to give us x. But this side, I don't know about this side. If memory serves right, I think that's going to end up being an inverse tangent. Let's see here. I'm going to look up a reference. What's the derivative of tangent? Actually, I'm going to say arctan instead of trying to type a -1 power into Google. Okay. That is what I thought. So, the derivative of tangent inverse of y would be 1 over 1 plus y squared. So if we can turn this into something that looks like that, we'll know we're dealing with a tangent inverse. So let's say x equals the integral dy. Let's factor out a k squared from the bottom. So we'll have 1 over k squared here in front. We'll have 1 plus y over k, but squared. And now it should just be a simple matter of 1u substitution to do this integration. So if we had u equal to y over k, then du dy would equal 1 over k, and dy would equal k times du. So we're going to end up with another k outside, and then we'll get, we'll have k over k squared times tangent inverse of y over k. Okay, but we don't want to solve for x because that's our independent variable. We want to solve for y since that is our function. So let's go ahead and cancel out one of those k's. So to solve for y, first we'll get rid of this. We'll bring it to the other side. K times x. We have tangent inverse of this stuff. So to undo tangent inverse, we need to take the tangent of both sides. Then we have y over k equals tangent of k times x, or y equals k times tangent of k times x. That one was really fun. I saw this and I knew we'd have to integrate 1 over y squared plus k squared, but I wasn't sure exactly how it would turn out. I just knew it would be interesting. Okay, I think that's all of those that I want to do. Okay, this should be fun. Do a little physics. Okay. So we have a half circle here. On the top half of this half circle, there is a uniform, linear charge distribution of plus q across its arc length. And on the bottom we have negative q distributed across that quarter circle. And we need to find the electric field at the origin. Okay, this should be fun. So let's see, electric field should be, if we add up all the little pieces of electric field contribution, that should give us this. So how do we write each field contribution? We'll use the field from a point charge and integrate across that line. So 1 over 4 pi epsilon naught qi over r squared, and the direction will be in the r hat direction minus r hat direction. Because if it's from up here, the r vector is going to point away from the origin, and if this has a positive charge, we want the field line to point back towards the origin. Now, how do we turn this into an integral? We need to write the r hat vector, I think, in terms of, well, hold on. So the easiest way that we would have to integrate this would be using angles. If we could integrate from, pi over 2 to 3 pi over 2. So can we describe that in terms of angles? I believe we can. And that's going to come from filling in qi. So, actually, we should call that delta qi. I don't know why I erased the q just to put a delta in front of it. So each small bit of charge is going to be the charge density times a small bit of length, delta L, and the charge density for each one of these is going to be plus or minus q divided by this arc length, and the arc length would be r times pi over 4. So lambda equals q over pi over 4, or 4q over pi, and the small bit of length is going to be r delta theta. Yeah. And I think that should give us everything we need. So is there going to be any problem if we now just write this as, we'll say negative 1 over 4 pi epsilon naught, the integral of, we'll turn this delta into a d theta, so 4q over pi 1 over r squared from here times r d theta in the negative r hat direction. Oh wait, no, I put the negative out here. Just in the r hat direction. Does that work? Or do we need to do something else here? Yes, we do. We need to write this r hat vector in terms of x and y, because that's going to give us a sine theta and cosine theta, which will actually affect this integral. So r hat should be it's going to be based on cosine theta in the x hat direction and sine theta in the y hat direction. Will that be of magnitude 1 though? I think so, because cosine theta, sine theta describes points that are on the unit circle, which are exactly distance 1 away from the origin. So this is still of unit length. So we're actually going to get two integrals here. Cosine theta in the x hat, sine theta in the y hat. We're going to have a bunch of stuff times the integral of cosine theta in the x hat plus the integral of sine theta in the y hat. Okay. Also, we need to break it up based on the positive and negative parts of the charge. So let's see here. We'll go ahead and simplify some of this. These 4's are going to cancel out. We could call this a pi squared in front. R divided by r squared will just be 1 over r. And we'll bring that q out here. So we're going to have the integral of cosine theta d theta for the x hat and the y hat. We'll have the integral of sine theta d theta. So let's see here. I think here's what we're going to do. We're going to say that electric field is E plus added to E minus. We'll do E plus first. That way we don't have to try to split up these integrals in line to account for the positive and negatives. And now I'm wondering if we need to actually use like pi over 2 to pi, or if we can just do 0 to pi over 2. If we do pi over 2 to pi, we're going to get negative values for cosine theta. And if we do that, that's going to mess with the positive charge. And all we're really adding up is an electric field strength that will point in, well, in the x direction it should point in the positive, right? The electric field lines show the direction that a positive charge would move, and if this is positively charged, a positive charge would move in the positive direction away from it. And then in the y direction we would expect it to move down. Oh, I just realized I wrote sine with nothing inside of it. So this we would expect to be positive, and this we would expect to be negative. I think we can just put those signs on it and do it from 0 to pi over 2. So, in the x hat, integrating cosine, you would get sine from 0 to pi over 2, which would be sine of pi over 2 minus sine of 0, also known as 1. So we're going to get 1 in the x hat direction here. If you derive to positive sine, then you integrate to negative cosine. So we'd have cosine of pi over 2 minus cosine of 0, also known as negative 1. So minus negative 1, you would get a plus 1 out of this. So altogether, these integrals are going to add up to just 1 in the x hat and 1 in the y hat. So that's, oh, I guess I should say it's minus q pi squared epsilon naught r x hat plus y hat, and then plus whatever we get for E minus. So let's fill that in now. E minus, we would expect the x direction to give a negative value and the y direction to give a negative value, because a positive charge would move down towards this quarter circle. So these are both negative now. You know, I think now that I'm accounting for these directions down here, this negative sign was redundant. I'm going to double check that after we finish this up and see if it makes sense, and then maybe change stuff if we need to. So once again, this is just going to give us a positive 1. So we would get negative 1 in the x hat. We're going to have this same magnitude out in front. So negative x hat. Which is what we'd expect. We'd expect positive charge to move to the left towards this negative piece. And this integral is going to give us a negative 1 again, which will result in a plus y. So let's think about what we have here and decide if it makes sense. So if you stick a positive charge here, it's going to feel a push away from the top, and it's going to feel a pull towards the bottom, only talking vertical direction. And since these are exactly opposite in their charge, it should feel effectively, you know, double the force it would from one of them. So we have double the y hat. And if these are all equally far apart from him, you know, there's a piece here at, you know, minus 0.1 that has a positive and negative charge. Those are gonna push and pull the same amount in the x direction, so those should cancel out. And we would expect the overall motion of a positive particle to be downward. So that negative should be here. Yeah. So we got it. So we can write this a little more succinctly. The x hats cancel out. So we'll multiply by 2 and slap a y hat on it, and that will be our final answer. So that is the vector quantity for the electric field at the origin from this half ring of positive and negative charge. That was fun. Let's see what's next. I think I did some of these integrals last week. Okay, let's try this. We have the integral of 1 plus cosine theta dx equals tangent of theta over 2 plus c. So this is given. then we want to find the integral of 3 plus 3 cosine of theta over 4 d theta on top. Oh, I wrote a dx there. Okay. So, first we want to factor out these 3's, of course. So we get a 1/3 out in front of this integral. And this relationship is only for regular theta, so we need to do a substitution here. We'll let u equal theta over 4, then du d theta would equal 1/4, or 4 times du would equal d theta. So we would get 4 over 3, the integral of du 1 plus the cosine of u. And that is what we have our formula for. That's going to be tangent of u over 2 plus c. But u is just theta over 4, so that's going to be theta over 8 plus c. And we could say this is 4/3 times all of that, so we would get 4/3 c as our constant at the end. But if we're going to check this against some initial condition at some point, we would just find c and it would compensate for that 4/3. So we can just leave it like that. Try another one like that. So given that the integral from 0 to 3 of 1 plus y squared on the bottom equals some constant k, find integral from 0 to 1 of 1 plus 9x squared on the bottom dx on the top. So the part that is throwing me off about this is the different boundaries, right? Also, using the fundamental theorem of calculus, this k should be equal to tangent inverse of 3 minus tangent inverse of 0. And how do we deal with that 9? It's not like it's 9 plus x squared where we can factor out the 9 and have our variable divided by a number, which makes for an easy fix with a substitution. oh, but 9 is 3 squared, so we can write that as 3 times x, but squared. Yeah, that's the trick. So we could let u equal 3x, then du dx would equal 3, and du over 3 would equal dx. So if that's I is going to equal 1/3 the integral from 0 to 1 of 1 plus u squared du. Now we are supposed to find I in terms of k. So we could say this is tangent inverse of 1 minus tangent inverse of 0. We want it to be in terms of k. So let's think about how we can incorporate that. So if k is this integral from 0 to 3, oh, also, our boundaries changed. That might take care of itself. So when x is 0, u is 0. And when x is 1, u is 3. It did take care of itself. So now this is exactly equal to k. So this is k over 3. And just for funsies, we can say this is, well, it's 1/3 tangent inverse of 3 minus tangent inverse of 0. And I believe tangent inverse of 0 is also 0. When it's tangent 0, it is 0 when sine is equal to 0. So yeah, this would be 0. So that means 1/3 k is equal to 1/3 tangent inverse of 3. So this k is actually equal to tangent inverse of 3. What is the number tangent inverse of 3? I don't know. Let's find out. We should, let's see. Tangent, you put in radians and get out a number. This, you put in a number and get out radians or degrees. I'm gonna go with radian mode. So tangent inverse of 3 is about 1.25 radians. Or if we do it in degree mode, it's about 71.6 degrees. So that's neat. And it looks like we are about out of time, so I think instead of starting another problem, I will just go ahead and end it here. So if you've been out there watching, thank you for tuning in to the Radical STEM Homework Help live stream. And hopefully, next time, you'll have some homework questions, because it's always more fun to help solve live stuff that viewers send in than it is to just solve random problems from a worksheet. So, until next time, have a radical day.